Yeah, this is the right class. Sit down. All right, so let's just have a quick recap on the Parzen window density estimation. So we wanted to have an estimate of P. We call it P hat of X. By the way, my handwriting is awful, so just quit. If you couldn't read, just let me know. I can explain it. So P hat of X here refer to the estimate of the density we want to have given certain x's, right? So suppose in 1D you have some x's comes from your data set D, and you want to find an estimate for these values, right? So for each of these bell-shaped curvature, sometimes they're called bump function. So a bump function has sort of this similar shape. And you already saw that by controlling a hyperparameter called gamma, you can control the way you underfit or you overfit your density, right? Just your distributions. And simply by using a cross-validation, you can maximize the likelihood of these two different distributions so that you won't underfit or overfit as well. So because if you choose a small a gamma here, you're gonna end up having an overfitted model, and on the other side, on the other extreme end, you're gonna have a large gamma, and then you're gonna have underfitting, right? So by doing cross-validation, you can understand what's going to be the appropriate gamma you can choose. All right? Yeah, I'll wait till you can write it down if you want. I don't know why the projector today turned yellow. It used to be white. All right, there was also another thing about Parzen window. So we were trying to find the answer to this integral p hat of x dx equal to 1. So the area that this estimate brings, so suppose this is the window with your estimates, right? So we want to make sure this area is equal to 1. That's why this integral should be 1. So if you have several bump functions, we have to normalize them. You have to scale them by 1 over n, so that it ensures the p hat estimate integrates to 1, right? So in this case, you have, I guess you had it last session, so you had 6 points. So the Gaussian kernel using Parzen window with 6 points, they're going to form a uniform density distribution, right? And we want to make sure this is equal to 1. So now, one of the better or more commonly used techniques in order to estimate the density in an unsupervised manner, because you have a bunch of data. Suppose they are in 1D, so you have a vector of x here. So you have some data here. You don't know the labels. You don't know what they are coming from, right? You just have them as they are. So you want to make sure you gain some information how the density of these might be, and then use this in order to cluster them, right? So one of the better techniques, since this comes from a distribution of data, one of the more well-known techniques are called Gaussian distribution, and they're using mixture of models to do that. So before starting that, I'm just going to have a recap on the univariate and the multivariate Gaussian distribution. Since we thought this portion of the course might be involved with a little bit of more statistics, in this week's tutorial, we asked the TAs, so they're going to have more recap on that, and then they're going to put some more reference online as well. So a Gaussian distribution, or sometimes we call it normal distribution, in one-dimensional space, so in 1D, so these are some examples. So you have 4 different distributions. Each of them, they have their own mu and sigma square, right? Mu is the mean, and sigma square is the variance. So we can define a Gaussian or a normal distribution in one-dimensional space by a random variable x, and we define it by this n form, which is representing normal shape, by these 2 hyperparameters, right? The first one is mu, represents the mean of this distribution, and the second one is the standard deviation. So this is the standard deviation. Similarly, if you have the standard deviation as sigma here, so you can have the square version of that as a variance of your model, right? So here in this figure, you have 4 different distributions. If we are talking about the Gaussian distribution or a normal distribution, normally the one in the middle, so just think about the red one here, okay? This one, okay? So normally the value in the middle represents the mean, or the mu here. That's why it's 0. And normally in a normal distribution, this has a maximum value. And also, this window here represents 2 sigma value. Why? Because the standard deviation comes from each of your x's. So x's might be here, 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 or here, right? Each of the x's minus the value that mu represents. In this case, mu was 0. So you're going to have 1 sigma, and then the whole window might become 2 sigmas, right? So this area here is going to be represented by 2 sigma. And depending where you have your mu, so in the green distribution, for instance, you had mu equal to -2, so that's why this one was -2 here, right? And then the rest of the points in a normal distribution can be defined by mu minus sigma or plus sigma, and then you have your confidence level 68% or 95%. So I'm not going to go into those details. But for now, you just know that when you have a normal or a Gaussian distribution, you can define it this way. So n of x, mu n, sigma, right? These are the hyperparameters. All right. And the probability distribution that these points generate is going to be computed this way. So this is what we call it a normalizing constant. Normalizing So again, we want to make sure that the area becomes 1, and you have a quadratic form of exponential. So this is e raised to this value, right? So you have x minus mu squared divided by the variance. So now, when we have this model with these hyperparameters, we can, let's see, sometimes this my presentation, yeah. So when we have this model, we can sample from this model, right? And we can estimate the mean and also the variance. That's why the maximum likelihood estimate for mean is going to be computed easily with the summation of your x's divided by the numbers. So if you have 10 of those, for instance, the variance, that's why we had hat here. So there are the estimates of those. Each of the x's minus mu hat squared, right? So suppose you sample it for 10, the 10 times do the same, and then you have an estimate of the mean and also the variance. Okay? Any questions so far? Yeah.
So the values of x that we're going to plug in to get the mean and the variance, like the values that the distribution is generating, we're assuming that it's a Gaussian distribution.
Yeah. So suppose you have a Gaussian distribution with 2,000 points, and you want to have an estimate using 10 points. 10 out of those 2,000, right? So you sample it 10 times, and for that sample you can have mu hat and sigma hat, right? But you want to make sure this is as close as the real mu, right? That's why. All right, so that was the sort of watered down univariate Gaussian version. So if you go for a vector space, higher dimensional and multivariate, so multivariate Gaussian distribution, so you're going to have again a bell-shaped form. So similar to a univariate case, a multivariate Gaussian model in a vector value, that's why we have this form here, comes from, we can define it as a normal distribution with this n for our vector of x in higher dimension, and we're defining the mu of j in vector space and also the sigma j. And this sigma comes from the covariance here. So just like before, if you want to have a probability distribution of the x's in vector space, we can define them by this format, a normal distribution of x given these two hyperparameters, right? So let's see how we're going to compute this one. Just like the univariate format, so we have a normalizing constant here. And this value represents your determinants of the covariance matrix. And then you have again a quadratic exponential form, but since we are in vector space, we're going to show it in a transpose version of this matrix, an inverse matrix, and multiply it by this column measure. So the first one is a row vector, this one. The subtraction of each of your x's minus mu. The second one is your covariance matrix. So suppose this is in D, so the size was D. The covariance matrix has the size D multiplied D. And the last one is a column vector matrix, right? So can anyone guess if you multiply these three, what's going to be the size of the output? So you multiply a row vector D size, and then D by D, multiply that by column. What's going to be the size of the output? What do you think? Yeah. That's why you have a scalar value here as your probability, right? This becomes a scalar value. So using this formula, you can compute the probability of this distribution in higher dimensions. So you've already seen some other examples before. If you slice this like from this side, so you're going to have like contours of this shape. Some of your data are inside, some of them are outside, right? In 2D format. Yeah, we call it contours. You can slice it this way. And just like before, you're going to have your mean and covariance in vector space, mu1 up to mu k, and also sigma 1 up to sigma k. And again, if you want to estimate the mean, now we're going to have an expected value here. So that's why this E is referring to Ex equal to mu I. And also for the covariance, we have multiple features. For instance, x1 and x2. That's why you have covariance in vector space, and that's going to define your sigma I, right? So now in Gaussian mixture models, or GMM, we are trying to use this sort of distributions in order to estimate our density. So when we have some x's from our data set D, x1 up to xn, so we want to make sure we fit them with the best curvature that comes from a Gaussian distribution model, right? Which one? Yeah. Oh, that one is the inverse one. And the inverse of this sigma is going to be again d plus d. D multiplied, yeah, sorry. Okay. So yep.
What is that 2 pi d over 2?
So it's again a normalizing constant. So we want to make, so this is like the square root of that. So we divided by 2 is the square root of that point. It's a normalizing constant. We want to make sure the area that this defines goes to 1. That, so remember in Parzen also we had px dx. So we want to make sure this integral goes to 1. So you need to have a normalizing constant here. Normalizing constant.
So it's 2 pi to the power of d over 2.
D divided by 2.
To the power of? Is it?
Yeah, to the power, right. Oh yeah. So it's to the power. So it's as if you go like this, right? Yeah. It's good you asked. So this is power. All right, so in Parzen window estimation, density estimation, you had a non-parametric model But now we have parameters to play with, right? We have the mean, we have the variance, covariance. So it's a parametric form of distribution. So we can play around with defining a more fine-grained estimation of the density. And that's one of the key differences between a Parzen window estimation and GMM. Okay? So GMM, we call it a parametric version of Parzen. And again, PowerPoint. So in Parzen window estimation, we place a Gaussian bump at every data point. But in GMM, we place k of those, k bumps, at center of your moves. Okay? So it's as if you have some data here. Here. So our estimate would become something like this. Right? That would be your mean. Last one maybe. It's their means, right? All right, so now when we have a bunch of data, we don't know the label, we can just feed them into their own respective Gaussian model, right? Using their mean and other hyperparameters. It's as if we, for instance, here we have this 8 data in blue, and we have 2 features in 2 equal 2 space. So cluster S1 will be represented by this bunch of data, and S2 will be with these, right? All right, now let's talk about a very important point about clustering using GMM or Gaussian models. So when we have, in clustering, since we are dealing with unsupervised learning, so we have some data. I'm just going to show it in 2D maybe. So you have this bunch of data, right? You don't know their labels. You don't know where they come from, right? You don't know their source of labels. But using mixture models, and also, yeah, we don't know the source, but the only thing we can guess, we can calculate the parameters of the respective Gaussians, right? So this Gaussian model could be defined by the hyperparameter of mu and covariance, or in a univariate case with sigma or sigma 2, right? The only thing we can do with this data is calculate these parameters. This is what we can do. And using this, we can guess whether a point is more likely to be belong to any of those clusters. So just say my final clusters were like this, right? And then I can estimate using these parameters that I found from these two, that how likely is it so that the point can belong to this one or this one, right? And that's the essence of unsupervised learning. The question? Right? And that's why we need to compute these hyperparameters and best fit them using a Gaussian distribution, right? Yep.
So the first step to this process is to do the k-means clustering on your data set, and then you do the Gaussian.
That's a good point. So actually, there's an algorithm you're gonna see in your next lecture. It's called EM, expectation maximization, right? It's the optimized version of k-mean. So k-mean is sort of a special case for EM. In EM, you use Gaussian distributions. In k-mean, you just use. So in k-mean, if you recall, that was a very good point. So when you have this data, you cluster them, just like the egg and chicken problem. So you start with the random clusters, and then using their center point, defining by mean only, you would compute the Euclidean distance of a new point, and then you would understand, okay, this is closer, so I'm going to put it in this cluster. This is further from this, so I don't have to put it there. But here, not only we use the median, but use a Gaussian distribution, right? Using the sigma, the variance. So k-mean, in a way, is a special case of EM that you're going to learn later on. Right. Yep.
So for the hyperparameters of the Gaussians, the mean will be like a vector.
That's right.
And we basically check to decide which cluster to put the point in. We basically define the Euclidean distance between the point and the mean.
In this case, when we have a distribution, Euclidean distance simply won't work the best. In this case, you have to find a maximum likelihood. And you have to compute the in-sample error, in, and all those stuff. I'll go with that, yeah. Good question, yeah.
So one of the difference in this one and k-means is that this one gives the soft output where you have like probability being a k with like cluster.
Yeah, yeah. That's right, yeah. K-mean is sort of more flat, you know, right. Also, I'm trying to not jump over EM that much, but EM has also another version that you're going to learn next session as well. So it's called soft decisions. So it supports intertwined clusters. So you have overlap with clusters. It has another version called hard decisions. So you have disjoint clusters. So you're going to learn both of them next session. But for now, we're going to just see how we're going to use these fundamentals of Gaussian models in order to best fit the distribution, right? So GMM accounts weights here a Wj with a Gaussian kernel so that the sum of those W's become 1, right? So suppose your data comes from a data set D, all in vector, x1, x2 up to xn, and all of them are coming from a two-dimensional space of R. So when you generate your data, your xi's from this IID, and you have a probability of x, so this would be equivalent to having a mixture of Gaussians. Does anyone know what IID mean here? All right, I'll have a slide. I'm going to talk about it. So IID stands for identically distributed and independent, if I'm not wrong. I always something like I always forgot about it. So it just defines your two properties for your distribution. I'll talk about it in the next slide. So here you have a bunch of data in blue, and d is equal to 1. So you can define them by 3 different bumps, right? Or curvature shape, bell shape. Each of them are having their own mu and sigma, right? First one, second one, and third one, right? And using Wj, you can weight at these 3, so make sure the overall area, again, becomes 1. So our Px, the probability of x in vector space, is equal to the summation of all j's from 1 to k, and you have to multiply this to this value, which was a scalar again, and you're going to have the final Px. So W1 multiply by the first one, W2, W3, right? Yeah, that's a mixture. And my handwriting is awful. And this triple equal represents equivalency, right? I'll upload this slide later on. You can find it on Quarkus as well. So no worries. All right, so let's talk about, and yeah, just like I mentioned, so the W's must be positive, otherwise there won't be any shapes, and the summation of all those W's must be equal to 1. It's a normalizing constant.
So when we find the probability for all the points, possible we get 1. We integrate this function over.
This is just scale each of the distribution in a way that the final area becomes 1. Yeah.
So if you're in more than one dimension, like the covariance is pretty different. So like the kind of the orientation of each Gaussian will.
Yeah, could be. Good point. Yeah. All right. So IID. So it's identically distributed and independent. So what does that mean? So you have this estimate. This presentation on Mac, Microsoft. All right. So we call it identically distributed. First one. And then independent. So these words. So first of all, we call it when all your x's are initiated from this. So we call it identically distributed if and only if you have f of x of x. For each of the x's in R space, you can have the equal to fy of x, right? And remember, this is if and only if, so comes both directional. So they are identically distributed, and we call it independent if and only if we can break these two, f of x of y, to a multiplication of 2 f of x of x and f of y of x, right? So if these two conditions holds in both directions, so we call that IID. So we use density estimation, and And one of the common application of these techniques that you're learning in unsupervised learning is for anomaly detection, right? So you can expand it to malware detection. You can expand it to antiviruses can deal with that. Or when you want to assign jobs to task scheduler and you want to detect those that are taking more of the resources that needed. So any anomaly detection, you can do that with this density estimation. All right. That was a P. All right, so let's again talk about that W that you already saw. So in vector space, we can define the mean and covariance this way. You already saw that. And we use this W from W1 up to WK, depending on the number of your estimate, right? So that we normalize each of those normal or Gaussian distributions using their own respective mean and covariance. And this X in vector space could belong to any of those, right? That's index n, if you're wondering. All right, so now let's see how the process will unfold. So when we use a GMM, how are we gonna define the maximum likelihood? How are we gonna optimize it, and how are we gonna find the best fit for our each of those distributions, right? So just another recap. By the law of the total probability, so if you want to compute the conditional probability of this, which comes from this normal distribution, so you have your x's, vector space, with mu and covariance, you can define this by the summation of all probability x given j, so the condition j, multiplied by the probability of j itself, right? And this will be equal to the summation of all the j's from 1 to k, and then your w that we define, and normal distribution, the probability that this one gives you, right? Using these hyperparameters that we had. Yeah.
P of j is the first argument, wj. P of x given j is the second argument.
Right. Right. Yeah, but just yeah. We can interchange them, right?
Yeah.
And this exactly defines you how to start to find the maximum or maximize the likelihood of best fitting your points using a Gaussian distribution. All right. So now, given our data set D, which we don't have any label for those, we have a bunch of x's in vector space. So what we need to do is find our hyperparameters, right? Our parameters that we need, because this is a parametric model, wj's, muj's, and covariance for all the j's from 1 to k. And just like before, you had a neural network, we can define the whole thing as our model parameters with omega, right? So using these model parameters, you have to use them in a way that maximizes all those probabilities that you just saw in the previous slide, right? From I to n. So this should be maximized. So, since we most likely want to minimize in our optimization problems, so how are we going to turn this problem, the maximization, to a minimization, right? So, and this will give us the E in of omega, right? In the sample error. So, changing this minus log of that, it's going to turn this maximization to minimization problem. And just like before you saw in this square methods and neural network, so now we have to compute the minus log of all these summations, w's, with their own respective distributions. And then this should be minimized. So if we minimize this iteratively or at one shot, we're going to find the best fit of an estimate of our data, right? So we have data here. And the real distribution was this, the P. And if we minimize it, so the dotted one is our P hat. So we want to make sure these two are as close as each other, right? So by minimizing this, we want to make sure the sample error is the least, and these two are sort of close to each other. How are we going to do that? And that's going to be your EM algorithm for next session. We could also use SGD, stochastic gradient descent, but since this function is so complex, the Gaussian for multivariate, it is not efficient enough to use a stochastic gradient descent, and that's why we use EM algorithm as an extension of k-mean to come up iteratively with the solution and minimize this. So we might start like from this. We want to start from this, and then the next iteration we might change it to like this, or this, and this. So iteratively we want to minimize this to the final solution. So if you plot the likelihood, so it's going to start from a lower point, and then it's going to hit the saturation point. This is the highest likelihood of your estimation.